So let's talk about how a transistor works. Here's my idea. First of all, we'll consider this diode, which has a very thin P junction or a P area, P doped semiconductor area, and this is an N doped area. So you know that the electrons over here, they have a natural tendency to go into this region. So there will be this charge buildup. So it will act like uh, a capacitor. It will create some voltage difference. Now let's connect this to a reverse bias. So this is the higher voltage, this is the lower voltage. So you know that electrons in this region, they will get sucked into this positive terminal, which means that the electrons over here, they are now like gone. So this region, this depletion zone, this will widen up. So essentially it acts like a capacitor and not as a circuit that can conduct electricity, right? So it doesn't act as a resistor or as a wire, it acts as a capacitor. So that's cool. So what that means is that without anything happening over here, you cannot have current flowing through this like that. But now think about it, what would happen if I say heat up this particular region? So I apply some, like, I don't know, flame or maybe light over here, who knows. So I somehow heat up this region. What will happen is that there will somehow be free carriers in this depletion zone. You know that generally there is no free carrier in the depletion zone because, yeah, I mean, it will experience field and it will start to move. But just consider an electron over here. All right, there's an electron. You know that the field is going to point like this, right? Inside of this, the field is pointing like this, and the force on this electron, that's going like this. So this electron, it will try to go to this side, to the N region, right? That's good and all. So what happens if electrons start migrating from the depletion zone to this region? Well, there will be a current, right? So that's good. If we somehow get the electrons from this P region, which is not having the depletion zone inside it, into the depletion zone, we are done. We will have a current, and that is done by photovoltaic effect. So like you can have photons hitting this depletion zone and doing this thing. But there's another way. What if we run a current across this such that the majority carriers are just electrons, and they are so high in number that the holes over here, they won't be able to accommodate all of them. So it's essentially just a lot of electrons filling up the P area, where usually we won't have any electrons at all, right? Usually it's just all holes, but now suddenly there's a lot of electrons in there. So these electrons, some of them at least, by chance, and well, we are talking about millions of electrons, so that chance, I mean, it's not insignificant. There will be a good current, right? So some of those electrons, they will jump into this depletion zone because there's no field, right? There's no opposing field. They can do whatever the hell they want to. So some of them, they will in fact jump into this region, and then they will get sucked towards the N side. Yeah. And that's essentially how a transistor work in theory. Now, obviously, this is not something that we can do directly. Like, how will you get a lot of electrons into this region, right? That's not a task that just passing current can do, because if you try to pass current like this, there's going to be holes that will get repelled and they will try to move in that direction. So the carriers actually will be hole in this case, and we don't want that. We want electrons to be the free carriers. So how do you accomplish that? What you do is you take another N doped area of semiconductor, and you put it next to the P thing. So now you have N, P, and N. And now if somehow we put current through this section, you know that's possible, right? Just forward bias this thing. So if we do this thing, there will be current flowing through this region. And you know what? All the electrons in this N region, they will migrate to P for that current to flow. So in this case, all of the electrons from this N region are jumping into P. So we have electrons in P, right? Now we just need to make them so huge in number that they overwhelm the holes over there. How do we do that? We dope it so heavily, and we dope this thing so lightly and make it so thin that the electrons need to be free to exist there. They cannot just fill into holes anymore, because there are just so less of these holes and so much of these electrons. All right, and now let's try to do this thing, right? So uh, now if we try to run a current across it, so with a reverse bias, that is, this is a forward bias, what do you think will happen? So we know that all of the electrons are now over here, and they are the thing that's carrying the current. And we also know that there's a depletion zone over here, just like we saw earlier. And by chance, some of these electrons will jump into this, and after that, well, it's current flowing through this loop. So that's an incredible thing. But this is not actually how transistors are, right? You don't have these two wires going across it. Instead, you have it in this form. So this is our small p slice, and you have these two n areas. And yeah, this thing is called the base. This guy, which is very heavily doped, this is called the emitter, and for good reason, because it emits electrons into the depletion zone of, this depletion zone. So yeah, and this thing is called the collector because it collects those electrons. So let's just label these: emitter, base, collector. All right, so first of all, we have a reverse bias in the base collector region, so this will be like this, and we have a forward bias in this region. Now this looks much more systematic, right? Yeah. Did I do that correctly? No, this is not a forward bias. This should be a forward bias. So notice that there will be current, so basically electron flow from here to here, and some of those electrons will jump into the depletion zone and they will get sucked up. So there's current going through these loops. So this is I1 maybe, and this thing is like I2. That makes sense, doesn't it? Now obviously the current flowing from base to collector, that's only a part of the actual current that went from the emitter to the base, because some part of that went like this. So yeah, we can represent this configuration like this. So this is the emitter part. There's current that it's like, okay, actually I should in terms of conventional current, it would be current flowing into the base, right? Because electrons are flowing like this, current is flowing like this. So current is flowing like that out, and current is also flowing like this in that direction. Okay, so from the emitter, current is flowing out, right? So we symbolize it like this thing. This thing is the base, which is connected to some voltage over here, some ground thing or whatever. Okay, whatever. And yeah, and this thing is connected like this to this cell. There's this another cell, and this should be cool. Okay, let's draw it a little neat, maybe like this. Okay, this is the emitter. Why am I drawing it like this? It should be like this, right? This is basically just the symbol that they will use to show a transistor. And you also need this thing for the collector, and there you go, that's your transistor. In this case, it's the BJT, that's the bipolar junction transistor. There's also a field effect transistor thing, but I won't talk about that. So basically what happens is, if there is current flowing across this loop, then there is automatically current flowing across this loop as well. So we can say that if we put an input current over here, there will be an output current over here. So we can like make a lot of logic through this small setup, and that's why you see transistors in all of the actual logical electronics logic gates basically. So yeah, that summarizes this thing. I know it's a very incomplete description of how this works. There might be more effects that I didn't consider, and this might be like very casual. It's not formal at all, of course. So maybe read some more stuff that will help you get clarity. Read the Wikipedia site for this thing. uh, Go read some stack exchange questions. Yeah, just research on this thing and convince yourself that yes, a transistor actually works like this, or at least it works in the first place. And of course, why it works, that's the question you want to answer, and I try to answer it the best I can at this point. So I'll see you guys in the next video.